Electric dipole. Electric dipole is a pair of equal and opposite charges separated by a very small distance. The electric field produced by a dipole is known as dipole field. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. Here minus q and plus q charge is separated by distance 2L. This is electric dipole. Electric dipole moment is charge multiplied by the distance between the two charges. Dipole moment P is equal to Q into 2L. The direction of the electric dipole moment is from negative charge to positive charge. And the unit is Coulomb meter. An electric dipole is the dipole in which the charge becomes larger and larger, and the separation becomes smaller and smaller. Now, electric field intensity due to an electric dipole. First, we calculate the electric field intensity at a point on the XL line of the dipole. XL point is point P, which is along length 2L. The distance of point P from center O of the dipole is X. We calculate electric field at P due to minus Q charge and then due to plus Q charge and apply principle of superposition. Here two electric fields are there, EA and EB. EB is greater than EA. That's why the resultant electric field at P is EB minus EA. EA is equal to 1 upon 4 pi epsilon naught minus Q upon X plus L whole square I cap, and EB is 1 upon 4 pi epsilon naught Q upon X minus L whole square I cap. We substitute the value of EA and EB, modulus of EB and EA, and we will get 1 upon 4 pi epsilon naught Q upon X minus L whole square minus Q upon X plus L whole square. We can take Q common from this and take LCM. It comes out X square minus L square whole square and then calculate it. Then we will get 1 upon 4 pi epsilon naught 2 Q into 2L X. Q into 2L is replaced by P. That's why it becomes 1 upon 4 pi epsilon naught 2px upon X square minus L square whole square. Direction of electric field is in the direction of EB. That's why it is in the direction of I cap. And EP is equal to 1 upon 4 pi epsilon naught 2px upon X square minus L square whole square I cap. If we take L is very less than X, then L is neglected in the denominator and you will get 1 upon 4 pi epsilon naught 2p upon X cube. Magnitude is this. The direction is in the direction of EB along I cap. Now electric field at a point on the equatorial line. Again we take dipole minus Q plus Q separated by distance 2L. OQ is the equatorial line. Equatorial line is the line which is perpendicular to the dipole and passes from the center of the dipole. The distance of Q from A is under root X square plus L square. BQ is equal to AQ. Now we calculate electric field at Q due to minus Q and due to plus Q. Magnitude wise the electric field is same, but the direction is different. Due to minus Q, it is towards A, means in the direction of QA, and due to plus Q, it is in the direction of EB. EB is the electric field due to plus Q charge. Now we divide this into horizontal and vertical component. Vertical component EA sin theta and EB sin theta, they are equal and opposite to each other. That's why they will nullify the effect of each other. Resultant is the sum of the two horizontal components. Because the horizontal components are in the same direction, that's why EQ is equal to EA cos theta plus EB cos theta. Because EA and EB is same, that's why we can take twice of E cos theta. substituting the value of EA 1 upon 4 pi epsilon naught to Q upon x square plus L square. Now we substitute the value of cos theta also, that is L upon under root x square plus L square. Now we calculate this 1 upon 4 pi epsilon naught Q into 2L upon x square plus L square to the power 3 by 2. Q into 2L is replaced by P. And we will get 1 upon 4 pi epsilon naught P upon x square plus L square to the power 3 by 2. The direction of EQ is opposite to the direction of dipole moment P. That's why we take here minus I cap, opposite to I. If we take again the same thing, if L is very less than X, then neglecting L in the denominator, and we will get EQ is equal to 1 upon 4 pi epsilon naught P upon X cube. The direction of the electric field is opposite to the direction of dipole moment P and parallel to the dipole moment. Again, if the observation point is far away or when the dipole is very short, then the electric field intensity at a point on the axial line is double the electric field intensity at a point on the equatorial line. Means EP is equal to twice EQ. Torque on an electric dipole in a uniform electric field. Torque is the turning effect of force. Let us consider uniform electric field. This yellow lines represent uniform electric field. They are equidistant from each other and in the same direction. Now we place a dipole minus Q plus Q, making an angle theta with the electric field. Two forces are applied. One is QE opposite to the direction of electric field because it is applied on minus Q charge. The force applied on plus Q charge is plus QE. It is in the direction of electric field. Quantity wise force is same, but direction wise opposite. One is plus QE, second one becomes minus QE. That's why the resultant force is 0. But the line of action is not 0. Line of action is not same. That's why it will form a torque. And the formula of torque is electric force into perpendicular distance. Electric force is QE, perpendicular distance is 2L sine theta. This vertical line is the perpendicular distance between this QE and this one QE. That's why Q into 2L is P and we will get tau is equal to PE sine theta. Then it becomes P cross E. Torque tau is equal to P cross E. Direction of torque is perpendicular to the plane which contains P and E. Unit is Newton meter. Now there are three conditions. First is if theta is equal to 0. Theta is 0, then sine 0 is 0, torque becomes 0. If theta is equal to 90, sine 90 is 1 and torque becomes PE, which is the maximum value of torque. If we take theta is equal to 180, again it is 0. Torque is 0. Now work done on an electric dipole in a uniform electric field. Again we take uniform electric field equidistant from each other. We take a dipole. Torque is applied and it wants to rotate it. Then what is the value of work done in rotational motion? dW is equal to tau d theta. Substitute the value of tau, that is PE sine theta, right? We rotate it from angle theta 1 to theta 2. So limits of integration will become theta 1 to theta 2. When we want to calculate total work done, then we have to integrate this equation. And the limits of integration are theta 1 to theta 2. PE will come out of integral of sine theta we apply, right? It is minus cos theta. Then we apply the limits theta 2 and theta 1. We will get W is equal to PE cos theta 1 minus cos theta 2. If potential energy is arbitrary taken 0 when the dipole is at 90. Suppose we take theta 1 is equal to 90, then cos 90 becomes 0 and theta 2 is replaced by theta. then the formula becomes U is equal to W is replaced by U, and this will become minus PE cos theta, because this theta 1 is 90, cos 90 is 0. Here this is minus. Now again 3 cases. If we take theta is equal to 0, cos 0 is equal to 1, and U is equal to minus PE, which is known as the stable equilibrium. If theta is equal to 90, U is equal to 0. If theta is equal to 180, then cos 180 is minus 1, minus minus plus, and U is equal to plus E, which is unstable equilibrium. So this is for work done, and work is stored in the form of potential energy. Thank you.